Hey physicists, in this video what we're going to be doing is continue with our venture into two-dimensional motion problem solving. So specifically applying the concepts that we have learned in the first couple of videos in the two-dimensional motion unit and see how we can apply them into more sophisticated examples. All right, so let's begin. So let's say you're on a cliff. You're on a cliff and the cliff is 50 meters tall. Excuse me. The cliff is 50 meters tall. And now I throw a ball or rock. Okay, I throw a rock at an angle of 30 degrees above the horizontal. So that's this little horizontal line. So I'm just going to draw the balls or the rocks. I'm going to just call it the rock's trajectory over here. Oh, all right. Sorry about that. All right. And I throw it with an initial velocity of, let's say 10 meters per second. Okay, so I want to find some quantities. First, I want to find the maximum height above the ground. So how high is this point? Then I want to find the distance from the base of the cliff that the ball has fallen. D. Oh, excuse me. And finally, I want to find the velocity of the ball, including like the angle with the horizontal. So I want to find the velocity of the ball right before it hits the ground. Okay, how fast is it moving? Okay, so this is a kind of more sophisticated since we don't have a completely flat surface. So we're basically combining the running off a cliff example from the last video and the range example from the last video as well. So we're combining these two and we're introducing some numbers. So it's a little easier to work with rather than variables. Okay, now let's begin. So our initial velocity is 10 meters per second. Now, the initial velocity will have an initial x component and an initial y component. And we know that these are both non-zero because, you know, the velocity vector is at an angle. So there has to be some y component, some x component. And our job is to find that x component and y component. Luckily, we know the angle. Okay, we know the angle. So if we know the angle, we can find v naught x by just taking the cosine. Because if you just have to imagine the component of a vector as a right triangle, as we have studied in the vector unit. So this will just be the cosine of the angle, and this will just be v naught y will be the sine of the angle. So we know that v naught y, we're going to solve for v naught y first because it's a lot easier to find the sine of 30. Because the sine of 30 is just 1/2. So the initial y component is exactly 5 meters per second. Now what about the initial x component? Excuse me again. Well, the initial x component, we're going to have to use a calculator. 10 meters per second sine, oh, not sine, cosine. My apologies. Cosine of 30. And that gives us about 8.66 meters per second. So that's our x component. Now, the x component remains constant in projectile motion, in normal projectile motion. So we don't have to worry about the x velocity anymore. The y velocity, well, that's a different story. So let's see if we can do part A. So the maximum height. So the y velocity changes because there's an acceleration. There's g. G exists. There's gravity. So gravity provides an acceleration that changes the y component of the velocity. And our job is to use the fact that there's an acceleration in order to find the maximum height. Now, if you remember from the one-dimensional motion example where we found the maximum height, you should see some overtones here. For example, what is the direction of the velocity vector right at the maximum height? Ooh, sorry about that. What's the direction of the velocity vector? It will be completely directed to the right, v at the top. It will be directed to the right. Okay, you can see that from the trajectory. And that's because the motion of the x and y components are independent of each other. However, at the maximum height, if you remember from that one-dimensional example, the free fall example, where you threw a rock up in the air, we saw that the velocity, at least the y part, becomes zero. It becomes zero because there has to become a point where it reaches its maximum height. It can't go up anymore, and then it starts to fall. So at the point where the y velocity is zero, that's the location of the maximum height. Okay, so what we have to do is find this location. So what can we do here? Well, what I would do most likely is we're going to be focusing on y, and what I would do is I would solve for the time first, because we know g, we know the final velocity in the y direction, that has to be zero. Okay, if we write our equations in the y direction, we know ay, that's just g. We know vfy, that's zero at the maximum height point at the peak of the trajectory. And we know v naught y, we just calculated it. Okay, we cannot use the other equation because we don't know delta y and we don't know t yet. So if we find t, we can then use the second equation. So let's find t using our first equation. Okay, so vfy is equal to 0. That means 0 meters per second equals 5 meters per second plus negative 9.81 meters per second squared t. And this should be a remedial equation to solve. Okay, very remedial. So it should be super easy, I hope. So we just solve and divide by negative 9.81 because t is 0.51 seconds. Okay, so that's the time. So at that moment, the y component of the velocity is 0, meaning that after 0.510 seconds, the rock reaches its maximum height. So let's use the second equation to find the change in height. And then using the change in height, we can find the maximum height above the ground. Okay, so for the second equation, it's quite simple. Because it's already solved for delta y. So I'm going to just write the equation. Just write the equation, and we get v naught y, 5 meters per second, times 0.510 seconds, plus 1/2 times negative 9.81 times 0.51 seconds squared. Okay, just have to cram that in there. Okay, now, let's calculate this value plus 0.5 times negative 9.81 times 0 squared. Okay, we should get a value of 1.274. Just double check. All right. So, okay, so again, delta y is 1.274 meters. Okay, we'll just round down. Now, it's 1.274 meters, so that's how high, that's the change in height from its initial position. So the maximum height, h max, will be 50 meters plus delta y, which equals 51.27 meters. So we have 51.27 meters. Okay, so that was part A. Part B, well, part B is a little more different. There are two ways, again, you can do this, but we're going to start with the given values first. Okay, there are of course more than one way to do this, but let's start with the given values. Excuse me. All right, so we want to find how long it takes for us to reach this point, because if we find out how long it takes for us to reach this point, then we can use the x equation. Delta x equals vxt. Delta x equals vxt, because vx is constant, so we can use this x equation in order to find the distance d. So how long does it take? Now we're going to have to use y again, because we want to find how long it takes for the ball to go from here to here. So what we do is we write our equation. That's number 1 equals plus 1/2 a. And then just upon closer examination, you immediately find out that it is, of course, a quadratic. And that you're going to have to use the nasty quadratic formula for this one. Okay, and it's actually necessary. So, because you can't do it without it, the quadratic formula, because v naught y is non-zero. So we're going to have to suck it up and plug in our values. Note that delta y is negative in this instance, since we're moving downward. So this becomes negative 50 meters, because the change from our initial point to the bottom is negative 50, equals v naught y, 5 meters per second, t plus 1/2 negative 9.81 meters per second squared, t squared. Okay. So we have this, and now all we have to do is plug it into the quadratic formula. T equals negative b plus or minus square root. Okay, it's always good practice to just write out the formula first so you avoid screw-ups when you substitute eventually. Now, our b value is 5 meters per second, so it's negative 5 meters per second okay, plus or minus the square root of b squared minus 4 times a times c. And note that c is positive because, again, we it's a quadratic equation, so c is positive. All of that over 2a. But, you know, the 2 and the 1/2 cancel, so we just have negative 9.81. Now, if you are clever, then you don't have to do a lot of work, because you can immediately find out which one, plus or minus, will give you the correct answer. And I can tell immediately that's going to be minus. It's going to be minus. Because if you look at the square root, well, 5 meters per second squared, well, the square root of that is 5 itself, but then you're adding something else to it. So the quantity under the radical is a lot bigger than negative 5. So if you add it, then you get a positive over a negative. So it's negative. The negative time doesn't exist. So if you have minus, then the negatives cancel. So I'm just going to compute the minus value because now I know that it's correct. So let's try to plug all of this in. So that's 4 times that 50. Just to make sure I'm plugging in properly. Square root of this, negative 5 minus this, divided by negative 9.81. And we get the answer, t equals 3.74 seconds. Okay, so it takes 3.74 seconds. It takes 3.74 seconds for the object to reach this bottom, the bottom from here. Okay, just looking at the y velocities. Now, because the time is same for both the y direction and the x direction, we can use the same time in our x equation. Delta x, which is d, is equal to vxt. And now we finally use the vx we calculated. 8.66 meters per second times 3.74 seconds. And that gives us about 32.4 meters. So the rock will strike the ground at about 32.4 meters away. Okay, now that's part B. So let's write our answer. Part B over here. Now our final question is VF. Okay, what is the velocity vector at that point? So that means it's asking us for the speed and its direction in terms of the angle. So it's asking us for this vector and its angle. So what is it? Well, how can we find the speed? Because the speed is easier to calculate, right? The speed is a bit easier to calculate. Well, they're both, actually they're both equal in difficulty, but we do need one value for both of them, okay? Because to find the magnitude of the velocity vector, we need both the x component, which is constant, so we already have that, and the y component, which changes, so we don't have that. Okay, we don't have the final y velocity at the bottom, but we do have the time. So for part C, let's use the equation number 1. Let's use equation number 1. So it's VFY V naught y plus AYT. So V naught y was 5 meters per second. 5 meters per second plus negative 9.81 meters per second squared. Meters per second squared times our time, 3.74 seconds. And what do we get? We get 5 plus negative 9.81 times 3.74. And we get negative 31.7 meters per second. So why did we do that? Well, if we were to look at the velocity vector, this is our final velocity vector, the VFY part is just this. We determined that's negative, so it's consistent with the visual representation. So we just computed the y component. We already have the x component on hand because the x component's constant. So if you remember from our study on vectors, the magnitude is just the square root of a squared plus b squared, the square root of the x component squared plus the y component squared. Okay, you can sort of think of it as Pythagorean theorem for vector components. Okay, so it turns out that the magnitude of the vector, so VF without the arrow sign, equals the square root of negative 31.7 meters per second squared plus 8.66 meters per second squared. And that equals, what do we get as a result? Oh, wait a minute. Okay, I didn't put parentheses. Okay, this squared plus 8.66 squared. Okay, and if we take the square root, we get a speed of 32.9 meters per second. So the rock moves at a speed of 32.9 meters per second. Okay, now we have just one more question, the direction. We were asked to find the vector. So what's its direction? And we can express its direction by its angle. By its angle theta. All right? By its angle theta with the horizontal. Now, how do we find this angle theta? Well, if you were to envision it as, again, as a right triangle, okay, envision as a right triangle, then you can easily visualize theta as a tangent or sine or cosine, as a trig ratio. Okay, and I'm just going to use tangent because we already found the answers to those. Okay, so Vx, Vy. Okay, so that is how you find the angle. Okay, so we get tangent of theta equals Vy over Vx, opposite over adjacent. Okay, and this becomes negative 31 0.7 meters per second over 8.66 meters per second. Note how the units cancel. So we have negative 3.66. So as a result, if I were to take the inverse tangent of that, or the arc tangent, we get theta is about negative 74.7 degrees. And here the negative corresponds to the angle is below the horizontal. It's below the horizontal. So, so that's what the negative sign means. So theta is negative 74.7. So the magnitude is 32.9 meters per second, and theta is negative 74.7. So let's just write those answers here. And we are done. We just found a lot of these quantities just by using component-wise definition of velocity vectors. Thanks for watching. If you have any questions, just let me know, and see y'all next time. Bye.